Okay, so in this video, I just wanted to run through intermolecular bonding with you, okay? Now, we have already spoken about ionic and covalent bonds. Now, ionic and covalent bonds are the glue or the links, if you like, that hold atoms together within a molecule, okay? Together within a molecule. So for example, like if you're looking at something like H2O, then you can see this is the glue here that's holding the hydrogen, that's an oxygen there, and this is the other covalent bond that's holding hydrogen to oxygen. If you look at something like sodium chloride, you have Na plus surrounded by Cl minuses. These forces of attraction between oppositely charged ions are called ionic bonds, and they're holding the sodium to the chlorine. So intramolecular bonds are bonds that hold atoms together within a molecule. Now on page 62 of your textbook, the definitions of these things are here, so you need to take those in your notes as you're going through the video. Now this is different. That's intramolecular bonding. This is inter. Now if you try to remember all the E's, so between molecules. So intermolecular forces are forces that hold, or that forces that exist between one molecule of water, say, and the next molecule of water. So really important that you differentiate the difference between intramolecular bonds and inter. So intra, again, hold atoms together within a molecule. So they're either covalent or ionic bonds. Intermolecular bonds are the forces of attraction or the bonds between one molecule and the next. So if you have a molecule of water here, and if you have a molecule of water over here, and if you have a molecule of water over here, then intermolecular bonds are between one molecule and the next molecule, between molecules, okay? So you'd need to write the definition of intra and intermolecular bonds in your notes and use those examples that I was using there to kind of reinforce that for yourself. Now, there are three types of intermolecular bonds that we need to know about, and you wouldn't have met these before. There are van der Waals, dipole forces, and then the third type of intermolecular bonds are hydrogen bonds. So these are all now intermolecular bonds, and we need to know a little bit about each of them, and you need to know where they'll arise. So the first one we're going to talk about are the van der Waals forces, and these will only happen between, remember all of these now are intermolecular forces, so all of these types of forces will arise between one molecule and the next molecule in a container, okay? Now, if we start off with van der Waals, and if we take something like the helium. So helium atoms 4 and 2. So if I draw a helium atom here, okay, then in the nucleus I've got positive, and around here you've got 2 electrons. You might have an electron here, you might have an electron there. Now at the moment, when the electrons are distributed like that, exactly opposite to each other, then there's no charge, there's no region of positive or region of negative charge. But that's very unlikely to happen, that the electrons will be exactly opposite each other. Most of the time, what you have, in fact, is you might have the 2 electrons. This would be your positive nucleus in here. The 2 electrons might be closer to the right-hand side of a helium atom. If that was the case, then that side would be slightly negative, because remember, electrons are negatively charged. The other side of the helium atom would be slightly positive, okay? So that's one atom of helium. Now, what about the next? If I had another atom of helium drawn here, the 2 electrons, for a split instant, they keep moving, you see, okay? So the electrons are continuously moving around the atom. So in this atom of helium here, 2 electrons are on this side, so that's slightly negative, that would be slightly positive. Now what's going to happen there is that the negative charge will repel, push away, and you will have another helium atom here, okay, slightly negative, slightly positive. Again, the 2 electrons are close here, and these will attract to each other. So that's where you have your van der Waals forces, okay. Another helium atom over here, okay, and again, look, you might have the 2 electrons here making it slightly positive, the other side slightly negative. Again, you'll have force of attraction between the slightly positive region and the slightly negative region. Now, the point about something like helium is that the electrons are constantly moving, okay? For one split instant in time, one side of the helium atom is more negative than the other, but then that will turn around and change again. So they're constantly moving from side to side. So you only ever have what are called temporary dipoles, okay? Now, a di implies two, doesn't it? And pole is a region, if you like. So a dipole implies that you have a region of charge separated by some distance. If the charge was in the same place, it would cancel out. So dipole is a region of charge separated by some distance. So in other words, you have a slightly positive area and a slightly negative area in an atom, okay? And it's the electrons moving that sets up these temporary dipoles, okay? Now, what about if I go now from neon to helium, say for a second? Helium is 20 and 10. So if I was drawing a helium nucleus, I'd have 10 protons in the nucleus, and I would have 10 electrons moving around. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do you notice about the number of electrons? You have more electrons in an atom of helium. And therefore, what do you think you would say about the slightly negative charge? Greater charge, wouldn't it be? Because you have more electrons. So you have a greater negative charge, and then in the next helium atom that you'd have, slightly negative, slightly positive. So say all the electrons are over here. Okay, then what we're going to say about the van der Waals that arise there now is that they're much stronger. They're much stronger van der Waals because you've got a greater temporary dipole in neon. Why do you have a greater temporary dipole in neon? More electrons, greater temporary dipoles because the charge is greater here. So greater temporary dipoles, more electrons, and therefore you have stronger van der Waals forces between one atom of neon and the next atom of neon. Now, if those van der Waals forces here between neon atoms are stronger than the van der Waals forces between heliums, then they're harder to break. They will take more energy to break. So one typical exam question would be, explain why the boiling point of neon is higher than the boiling point of helium. Now remember when you were in first year and you talked about boiling something, okay, you're turning a liquid to a gas. So if you're remember how particles of a liquid are arranged slightly close together, but particles of a gas are spread out and they're moving quickly independent of each other. So they have more energy, the particles have more energy, so they're able to do that. So what must you do if you want to turn a substance from a liquid to a gas? You have to break all these bonds, these intermolecular bonds between the atoms, and separate the atoms completely from each other. Neon has a higher boiling point than helium because neon is a bigger atom. It has more electrons, and because it has more electrons, it can set up greater or bigger, whatever you wanted to say there, greater temporary dipoles. Now, what's a dipole again? A dipole is a region in space, or a region that's a slightly positive, slightly negative region separated by some distance. So the negative and positive regions are not in the same place. So the regions of charge separated by some distance. Okay, so and they're still temporary though. So like for one split second in time, one side of the neon atom is slightly negative, but the next split second the electrons have moved around and the other side of the neon atom is slightly negative. So they're temporary, they're not staying like that, they're not permanent. Is that okay? So that would be a typical exam question to explain, explaining that sort of thing. Okay. So just to recap on van der Waals now. So what are we saying? Now remember, what are van der Waals? Firstly, so van der Waals are types of intermolecular forces. Okay. What does that mean? It means they are forces between one atom and the next, or one molecule and the next. So here you'd have van der Waals. Okay, one atom of helium and the next atom of helium, van der Waals. And the other thing is you draw van der Waals in dotted lines, not solid lines like the covalent bonds. They're dotted lines that you would draw. Okay, remember what we said. Bigger atoms, or bigger molecules for that matter, would have more electrons and therefore the region of positive and negative will be bigger. So greater, we're going to say that they have a greater temporary dipole, and therefore they will take more energy here to break that van der Waal than it would take to break this van der Waal here, okay? Now, one last thing about van der Waals. Van der Waals will exist between non-polar molecules. Now, this coincides a lot with the organic chemistry that you would have done. So alkanes, alkenes, and alkynes are all non-polar, okay? Alkynes, non-polar. What does that mean? It means that if you draw out something like methane here, CH4, we looked at the electronegativity difference between carbon and nitrogen, and between carbon and hydrogen, and when you do, it's less than 0.4. So it means that there's an equal sharing of the electrons here in the methane molecule. There is no permanent dipole. So what will happen is, if you have a gas cylinder or cylinder of methane gas, what kind of intermolecular forces can you have between the molecules? Van der Waals. So van der Waal forces occur between methane, one methane molecule and the next methane molecule, and the next methane molecule will be over here. So between alkanes, between alkenes, and between alkynes, you have van der Waal forces because they are non-polar molecules.